So today we wanted to talk about spectrum management. And the reason we want to talk about this is I got to say 70-80% of the calls that I get from customers saying, I just got my DFIN on my distro 4 and it's not working. Well, there's two halves to this, right? So, let's see here. You can make this screen go. There we go. Oop. We'll get there. So there's two parts to making your wireless microphone work. There's the radio signal, and that's the things that we make. That's the antennas and the distros and all that. So what we can do is we can give you a clear radio signal from your transmitter to your receiver. We can help get a very clear signal there. But just because you get a clear signal doesn't mean you're going to have a successful wireless mic. You have to find a clear frequency to put it on. So a lot of times when I get this question, well, I hooked up my new distro and, 6 of the microphones are working, but 2 of them aren't. Pretty good best choice is that those 2 are on the wrong frequencies. They simply won't work. Regardless of how you got to that choice, if a computer program told you or your built-in scanner told you or whatever, it's not working. And you need to move to a clear frequency. Because that's really that's the really only effective tool that we have. You're not going to block other things. I mean, you can build Faraday cages, but very expensive. So we have to find clear frequencies to operate on. When we have these 2 things, then we're gonna be good. So obviously, there's all the antennas and the distros and the cables and all that hardware that we make that's going to help you get the radio signal from the transmitter to the receiver. But helping you find a clear frequency, you really need help from a computer. You just can't guess anymore. If you got 1 microphone or 2 microphones, you might be able to guess. If you've got 6 or 12 or 24 or 48, you're going to be guessing for a long time. So let's just use some computer help here. We have this program, and we'll talk about it a little deeper down into this. But if you go to our website, on every page, there's a round button that says Performance Tools. Click on that, just plain rfvenue.com. And click on that, and it'll take you to this wireless system builder, which will help you pick out, if you're buying gear, it'll help you pick out appropriate gear for your location. And if you already have gear or you're adding gear, whatever, however you've got the gear there, this is going to help you choose the best frequencies for that gear. Push the right button. So we have a lot of choices. There's actually wireless mics that can kind of work all over the place. But what we're mostly talking about is UHF TV band wireless mics. Yes, there's VHS. Yes, there's ISM 900s. There are DEC bands. There's 2.4. All that other gear is your second or third or fourth choice, unless you have a specific need that it takes care of. And, you can't really guess about that. You kind of need to know that. Otherwise, those things are troublesome for most people. So if you just stick in the UHF TV band, which now in the United States is 470 to 608, that's where all the good gear is, and that's where people use wireless mics. We think you're going to be able to make wireless mics work about anywhere. In the middle of Times Square, I can make wireless mics work. It takes a lot more work than it does out in the middle of nowhere, but if we follow all the best practices, because wireless mics are much better than they used to be. When the FCC mandated changes to all this spectrum, they also mandated to wireless mic manufacturers some new rules that didn't use as much bandwidth, have tighter front ends, and therefore they're easier to tune in. They don't interact with each other as much as they used to. So the first thing you kind of got to know is where your TV stations are. because as a general rule, you're not going to overpower a TV station. 500 kilowatts from a TV station 100 miles away from you is going to kill your 10, 20, 30, 50 milliwatt wireless mic. So you got to work in the empty spaces. We just don't have as many empty spaces as we used to. This is Los Angeles. There's not a whole lot of space left if you've got an awful lot of mics and ears. Remember, we've always got to count ear. We're counting radios when we do a coordination. So it doesn't matter whether they're in-ear radios or they're wireless microphone radios. They are radios, and we have to consider all of them. So the thought is, well, why don't I just stick my microphones in these spots, in these empty bands? Well, that is where you have to put them, but you can't just put anything there unless you're extremely lucky. If you win the lottery a lot, go for it. But for the rest of us, knowing precisely what frequencies to use when we're using multiple radios. Again, if it's one radio, you don't need to listen to this. But if you've got a bunch, you've got 6 or 8 or 10 or 12, the more you have, the harder it is to work with. So whatever you've got's what you got. Okay, so the reason you can't just pick empty bands is because radios interact with each other and create intermodulation distortion. And the exact frequencies that intermodulation distortion can occur on is easily calculated by these programs. You don't want to do it by hand anymore, but the programs can tell you instantly, and they're going to know where all these other side bands are, right? So if you look at the one at the bottom, there's 2 microphones in the middle of that, but because they're reasonably powerful, they're creating a lot of overtones, of harmonics, and those harmonics are all radio stations. They're just garbage, but they are taking away other channels you could turn to. So, well, here you go. So, and it adds up very fast, right? It adds up factorially. So you multiply the next number by the previous numbers. So, when you're adding, 2 microphones, you get 4 principal harmonics. When you add the third microphone, you're not adding it to 2 microphones, you're adding it to 4. So you get 12. But by the time you have 8 radios, you have over 40,000 identifiable intermod frequencies. Now, most of them sit way down in the noise, and they're not active, and they're not really very problematic at all until you move over 2 feet on the stage and get 2 feet closer to your singer, and then they all shift in their levels. So as you got 6 or 8 or 10 or 20 people walking around a stage, you've got a soup here going on. You've got all these things, just depending exactly where you are. So the frequency coordination programs all consider those things and pick the best spots. So here's some things you kind of some rules of thumb. When you have analog wireless devices, they should be about 300 megahertz apart. They don't absolutely have to be that, but that's a good practice. You might be able to actually work with less than 200, but it's risky and it's problematic, and just don't do it. Digital, you need more space. If you have both analog and digital wireless microphones at the same time, treat them all as digital. Okay, that's the best practice. Again, there's best practices and there's what you can get away with. What you can get away with, you've got to be lucky. Best practices are going to be just that, the best thing you can do. So if we look at those two, graphs at the bottom, we can see that lower power creates lower IMD. So here's 2 microphones or 2 in-ear monitor transmitters. You can see if you transmit at 10 milliwatts, you can see what the residual noise from intermod looks like. And if you transmit same mic, same place, they're the same 4 mics, but you raise the power level, then you get considerably more interference. So, You almost never need the power level. I know it seems like you just want to have as much power as you can. You can power your way through. Probably okay with one microphone. Or for people that have to, if you're planning on going 300, 400, 500 feet, that's a different story. But most of us are working on stages that are 40, 50, 60, 80, 100 feet wide, distances like that. We're just not trying to go 300 or 600 feet. So if we can keep the power down, so anytime we can turn down the power, we eliminate more and more of this intermodulation, which opens up more and more clear space. Okay, so this is a tool that we updated and made real big changes to, because now this does frequency coordination. So let's take a look at this. I'm going to go online and actually be live. So what you're going to do is put in your address, your street address. You can pick anything, but you put where you are. And this is going to ask you if you already have wireless mics. So if you already own 6 or 12 or 24 wireless mics and you're just trying to get a frequency coordination, you simply tell it what brand you've got. I'll just pick something. Whatever. I got SLX. I'm just picking up a brand. So let's say I've already got 4 of those mics. So I'm adding those. And let's say I'm going to buy some new mics and some new ears. So let's just say I need 4 more wireless microphones, and I'm also going to buy 4 in-ear monitors. So you can twist this to however you want. Okay, and this is going to tell me what my best, if I need to buy new microphones, this is going to tell me the best choice for my geolocation. Right? So any from this list. You can sort this list if your favorite microphone is, whatever brand you want. Let's say it's Audio-Technica. That's fine. So this is now going to tell you, move those up here and tell you these are the blocks you should buy in Audio-Technica. In the same way, if you're going to do in-ear monitors, you can pick whatever you want. I'll just pick something here. Let's just pick this one. And so now this is telling me my existing mics, the new mics I want to buy, the new ears I want to buy, and it didn't like those. Let's pick something else. Did I break this already?
I think you just have to pick the mics up top there, Don.
Yep, sorry. Okay. So now this is going to, based on my geolocation, I can put the name, this is the name of my church, school, nightclub, whatever it is. I can put this up here, and this is going to give me the best choices based on the information this knows now. What this knows now basically are the fixed transmitters around you. Okay, so this doesn't know, if you have an X-ray machine on your stage, this doesn't know that. If you have 27 radios that you didn't tell it on the other page, this doesn't know that. So you have to let it know that. But this is going to tell you where your mics are. Oh, see, I've got one that's invalid. So this one isn't going to work. I'm going to need to buy another mic or switch these or something. If I've already got these 4, I probably need to change this one and open some new frequencies, and then these are my ears. So you go back up, and this is all color coded. So this is going to pick you the best starting frequencies. So I expect this to be very, very, very good unless you know some reason why it won't. If you're trying to run this in a military airfield, good luck. If you're trying to run this around, I don't know, huge industrial machinery or in a hospital full of X-ray machines and MRIs, I don't know what's going to happen. But almost nobody does. So if you're just worried about your school, your church, your nightclub, and you're not right across the street from an airfield, this is probably going to give you a very, very good, picking numbers out of the sky. This is going to get you 95, 6, 7, 98% as good as it's going to get. Doesn't guarantee it's going to work, but this is a really, really, really good choice. Now, if you have a scan, now that makes this even better, because now it not only knows, well, let me go back. Maybe some of you didn't catch this. Where the dark red is, those aren't going to work. Those are television stations. So you have about a 1 in 10,000 chance of working there. It's not going to work. Just move on. You can also do, well, you can upload a scan. So if you've got a scanner and you can save the scan as a CSV file, you can upload it onto here, and it will, with even more precision, give you these numbers. You also can do some band planning. We'll talk about this a little bit farther into this as we're talking about working with mics and ears together. But if I needed to see well, this is a good example, because these Audio-Technica in-ear monitors are the only ones I know of that will tune all the way in the US band. You can tune from the very lowest frequency to the very highest frequency available. So if I wanted to restrict these and say, I want these to tune from 580 to 607, I could recalculate, and it's going to move those. See, I put them all down at this end of the band. I got all my mics at this end of the band. I got all my ears at this end of the band. That's very helpful, and I'll show you why in a minute. So you can recalculate any of these you want. If there's some reason you need to lock out a specific frequency, you do it right here in the band planning. So you can pick any of these frequencies you want and narrow their ranges. Okay, so that's handy sometimes. So I would also recommend that you go back up, and when you do this, this is your personal scan right here. So if you save this link right here with that horrible code at the end of it, that's this one. You can go back to this next week, next year, and see this. There's some other things up here. You can email it to somebody. You can export the frequencies. If you have networked microphones, you can export the frequencies to Wireless Workbench or Audio-Technica System Manager. So there's a few choices here. So anyway, this is like a really, really good way to do this. Now let's see if I can get back to my program. Where am I? There I are. Okay, so we went through that. One of the things, though, that'll make it easier. So these days, we have interferences we didn't have before. We have video monitors. You know, everybody's church has a video monitor up. Every nightclub has 27 video monitors up. Every boardroom. Everybody's got, that, and they contribute. They are wireless microphones that power supplies because of just the way they are. They transmit RF. That's all down here on the bottom end, and then all up here in the top end, that's T-Mobile 5G cell phones. So those things mix with your microphones, right, and create intermodulation. All radios on the planet, you're actually interfering technically with every single radio that's turned on the planet, even if it's 1,000, 5,000 miles away. It's so far down in the noise, you're not going to find it, but it builds up. It builds up, and that's what all this garbage is at the bottom down here. So you want to get past this. There we go. So if we put bandpass filters in, you can look at how much I cleaned up that signal. So obviously, I've got a lot more open spaces here to tune to. So you just can make it easier on yourself to begin with by adding the bandpass filters. So I want to talk about the scanners that are built into receivers. If you're scanning with your receivers and you're going directly into Wireless Workbench, or you're going into Audio-Technica Wireless Manager, your receiver will scan and send that information to those programs, or you can save it and you can put it back in Wireless System Builder. But you can only see what that radio can tune to. So you're using blinders. So if I scan with my radio that only tunes a block that's this wide, whatever it is, that's the only data I'm giving the program. And so the program is going to calculate a result based on the data you give it. If you have a regular scanner, not only can you scan the whole band, the whole 470 to 608, but you can scan beyond that. And that's important because, as you can see, I've drawn the lines there where that's the band in between that. But you see there's radios on both sides of that. There's radio signals on both sides of that. And those radio signals above and below what you're trying to do are mixing with your wireless microphones and raising that noise floor. So if you don't, let me back up. All of these frequency coordinations, and by the way, they all use the same math to get to the answer, right? So the math is simple. It's been around for years. It's very straightforward, and everybody uses the same formulas to calculate where this ought to go. It's just the way you input data. But by giving the calculator more data, it can make better decisions because it now can count that. It knows that out of band information is going to interfere with your in band stuff. So it's going to make probably always different choices. It depends where you are. This every time you do this is unique, right? If you put it in your church and you go down a block, half a block, and you got to go to another church, you'll get a different answer because every place you are makes this at least somewhat different. So when you can use a regular scanner, we recommend that you overscan, that you scan, 30 or 50 megahertz either side of where you want to operate. Now, maybe you only want to operate in block H, whatever it is from Shure, that's between, let's say, 530 and 560. Then you need to at least measure, 50 megahertz either side of that. But if you use the receiver, it will only measure in that block. So that means you probably won't get as good an answer as you can get. When you use, the other thing is people use the built-in auto scan functions on their receiver. Well, that's better than nothing. But here's what happens when you do that. You have a limited scan. So like the red, I can only look in my block, and inside my block, it's going to pick from presets that it has. So it doesn't have every single frequency available. If you take a standard block from Shure, Sennheiser, or anybody, the block goes from a low number from 500 to 550, let's say, and if you go to their preset blocks, they probably have 8 sets of pre-selected frequencies, which are good to use, but those may not be the frequencies to use where you are in any of those sets. But that's all your built-in scanner is going to do. It's going to give you the best of the presets that are there, which probably aren't the best thing that it could be. So it's going to give you limited results. It's better than completely guessing, but if I had to pick numbers out of the air, that's going to get you, like 50% of the way of the best possible solution, which could certainly be enough. But using something like Wireless System Builder, which is free, you don't even have to download it. So you're able to use that. It's just at our website. Or you just go to rfvenue.com and click on the button. That means if you're out on the road, you can do this with your phone. You don't have to have a computer. You can do it with anything. So that's quite handy. The bandpass filters we talked about a little bit, and because they eliminate stuff above and below whatever frequency that's on them, there's a low number and a high number, and they interfere. They reduce the RF above and below those frequencies. So they don't have to match your gear. Your gear just has to fit inside the top number and the bottom number. Now, we made this easier because we've now just made 2 universal filters, and these just work everywhere. So the green one, 470 to 608, that's for North America, US, Canada, Mexico. I'm not sure how far it works into Central America, but basically North American frequencies. The other one, 470 to 698, pretty much is what the rest of the world can use. There are still some places that go above 698, and almost all of those are on timelines to reduce that frequency. So some places they can go up to 800, but there's probably laws on their books already that those are changing. So you might as well get where you're going to have to be in next year or the year after. Anyway, either of those filters just plug in, and they work with every brand of mic at every frequency within those limits. So that makes it really simple. You don't have to worry about buying the one filter and then, well, now I can't add a new mic because it's outside the band. If you just buy these universal ones, you won't have to use these specialty ones anymore. Okay, so let's talk about spectrum management if you're using wireless mics and wireless ears. So you have to remember these are all radios. We have to deal with all of these at the same time. We don't just deal with getting frequencies for our ears. We don't just deal with getting frequencies for our mics because they interact with each other. So we have to do these both at the same time, right? Okay, so what you'd like to do, if you're buying all new gear, this is easy. If you have existing gear, this gets harder to impossible, just depending on what you've got. But anyway, what we would like to do is we would like to cluster all your wireless mics to one end of the band. I don't care whether it's the top or the bottom, and all your ears to the other end of the band. I want to separate these two as far as I can, right? Okay, and then what I'd like to do is, so if I move all my mics to the bottom of the band, I want to tune them as tightly in a cluster as I can. Now, that depends on where you are. So you might want to do it, but you're going to be left with what you can do where you are. But so because what happens is when I put these in a cluster, so I'm just going to make these in tens because even I can count tens. So if I can put all my microphones between 500 and 510, and I can tune all my in-ears between 570 and 580, let's say. What happens is the principal amount of intermodulation, the most damaging part of the intermodulation, is about the same size as the cluster. So we add that above and below what we're actually tuning to. So in the case of the microphones, we're also, pretty much screwing up the space down to 490 up to 520. You really should treat this as though you're working in that big of a cluster now. And the same way with our ears. So if we're in a 10 megahertz cluster, we add 10 to the top and 10 to the bottom. But that leaves me a nice big space in between. This is what I'm shooting for, right? No overlap. Now, if you can't tune that way because your gear won't let you, if you've got some that tuned from 470 to 500 and some that tuned from 500 to 530, you can't tune that cluster tight. And it doesn't matter. Like if 9 of the microphones fit inside that, but 1 is outside of that, the cluster is as big as the biggest spread. Okay. You just treat it that way. It's essentially that. So if I had to tune all my mics, let's say between 500 and 530, then I'm adding 30 megahertz above and 30 megahertz below where I'm actually tuning. So I'm really kind of using the whole band from 470 to 560. Same way, if I had to tune my ears over 20 megahertz, I'm going to add 20 to the top and 20 to the bottom. What I'm concerned about is the space in between because now they overlap. Doesn't make it impossible, it just makes it harder. So we're trying to do everything, all the easy stuff. We want to do the easy stuff. We want to do the stuff that's easy and the stuff that's inexpensive. Because if I got to make 48 mics and 24 ears work in the middle of Times Square, I'm not doing it with $300 microphones, I promise you. It's going to take very expensive gear. But I can make it work. So it depends where you are. The more metropolitan of an area you are, the more difficult it is. The more, and there's plenty of stuff out in the sticks now that is being interfered with. Even though you think, I'm 100 miles away from a major city, there's just nothing here. Well, there's nothing you can see, but there are some other things that people like Microsoft are doing. Microsoft is doing broadband internet in the 500s, and they're active in 16 states, all in rural areas, and they plan to do the whole country. So things are creeping in with you. So anyway, best to get those clusters as tight as possible, and that gives you the best possibility moving forward. Let's see, how are we doing on time, Adam?
Well, 1 o'clock. Looks like we got a little bit of time left. I think we scheduled this 1:30.
Okay, that's fine. We got a bunch of questions, and if there's any more questions, there's anything I said that you don't quite understand, I'm happy to repeat myself. I repeat myself a lot, or further explain it. And we had a lot of good questions sent in this week. So, Adam, you wanna give me some of those questions, and we'll see what we can do about them.
Absolutely. I'll kick it off here for you. So, since we got a lot of questions, we had to shuffle them down to the best ones. So definitely keep sending in your questions. I'll try to answer them as best I can.
Well, and I hope we answered. So I hope we answered a lot of those questions inside this presentation. I know 4 or 5 of them are blended into this. Anyway, yeah, what do you got?
All right. So let's see. How to be confident about frequency, which was allocated by the software we use for analysis.
Okay. So the software is a best guess based on the data you give it. So the better data you give it, the better the guess gets. But just because you get that back is not a 100% guarantee it's going to work. So you set up everything to that and you walk test it. You turn on everything and test it. The next best thing you can do, and guys that are doing Elton John at the Enormodome, they also do a thing called wargaming. If you go to our YouTube website, RF Venue, YouTube's, there's a video on how to wargame. And it's a very good technique. It can take a really long time if you don't have a scan. If you've got a scan, you should be awfully close to getting that. But wargaming it is the next thing that you want to do, because that's going to test it in the real world, right? Because we always have, we have things that the building, reflections and multipath, the building's going to give us that may make some of these frequencies not work. So when you get a coordination back, some of those numbers are better than some of the other numbers, right? So they all should work, but some of them are going to work better than others. And so wargaming or walk testing, you really need to prove out the ones that are closer to the borderline. They may be a long way away from the borderline. They may be very close. But so walk test it and wargame it is the answer there.
All right, awesome. What key RF features are needed in RF devices in high density RF environments?
Well, so the good news is that, and I can't tell you the exact year, but the FCC, when they changed all these, when they restricted a lot of these bands, and they changed all this stuff, they also mandated manufacturers make better wireless mics. So newer wireless mics cause less interference. So the difference, pretty much, or one of the major differences between inexpensive wireless mics and less expensive wireless mics is how sharp they're able to tune. So when you pick a number, so when you set your mic to 505.250, it's not just a single line, it's a pyramid, and that number's the tip of the pyramid, right? So less expensive and older microphones, that pyramid is wider. So it's still sending RF energy at all these other frequencies. It just gets lower and lower as you get away from that center point, right? Very expensive wireless mics are very sharp. And these are now mandated to be sharper than they used to be. I don't know if they ever were mandated, but now they are. It's how, radio manufacturers now have to make tighter ones in place of the other ones. And that's one of the reasons that wireless microphones, forgetting inflation, are more expensive. It's harder to build them. It's more costly, but they're better. The other thing is, especially on some of the digital wireless mics, they have what they call low density mode. And what they've done is they are trading frequency response for bandwidth, how much space. So in low density, remember I said you should probably tune your digital wireless microphones at least 600 megahertz apart from each other. That would be in standard mode, high fidelity mode. In the other mode, the high density mode, it only takes up 300. And what they do to be able to work in a smaller space is they cut off some high frequency response and some low frequency response. So if you're only interested in speech, for example, then you can use the low density modes and you can get twice as many mics in the same space. That's the theory. So something like that. Honestly, you can try the low density mode might be better than your PA system. So you may not hear any difference at all. So if you get some of these newer mics that can run in low density mode, you can use more of them in the same space. But the other, how exactly was that question again?
What key RF features are needed in RF devices in high density environments?
Okay. So yeah, so restricted to, when you say devices, I assume you're meaning your wireless mic and not the external stuff. Obviously, the external stuff, better antennas, directional antennas, interference filters, low intermod combiners and distros. So distros and combiners cut down on that intermodulation. We talked about intermodulation. So if you've got 6 or 8 receivers and you've got their little whip antennas on all of them, you got these set up on a desk, you're getting a lot more intermodulation than you would be if you were using a distro, for example. Same way with your in-ear transmitters. If you're using a little whip antennas on every one of those babies, you're getting more garbage than you will if you resolve that in a combiner. You resolve those 4 transmitters down to a single transmitter, and then to a single antenna, and you'll get less intermod. That's part of the best practices too.
Great.
Okay.
Next one. What
Mhm.
IEM products do you see having the widest digital spectrum with insights on the importance of sound quality and low latency?
I don't know what you mean by digital spectrum. I think you mean the tunable spectrum.
Yes.
There is a pretty straightforward answer to that. The new Audio-Technica 3000 series analog in-ear monitors will tune from 470 to 608 in the US. I believe abroad they tune even wider. So they simply tune. Let's just talk about the US because I absolutely know. They'll tune to any frequency from the lowest to the highest that you get. So no matter where you get off the tour bus, you will have the best opportunity to tune. Where if you've only got block H50 and you pull into a city that's H50 is used up with TV channels, you're not going to have a good day. You're just not going to be able to compete. You need different wirelesses. So that those Audio-Technica 3000s will tune, from the lowest to the highest. So that's good. They are analog. Almost all IEMs are analog. And there's a good reason for that, because of the latency, which you talked about. So the problem is that when you run through anything digital, there's always some time delay. It takes some amount of time for a computer, no matter how fast it is, to crunch the numbers, right? And so when your in-ear monitor is digital, there's a very small time delay, a couple of milliseconds. But the issue is that for some people, so when you're the singer You have your microphone and you have your ears. You're hearing yourself through the bone that goes up to your ear instantly. And then you're hearing your in-ear monitor delayed a couple of milliseconds. And that causes comb filtering, it's phase shift, right? So it begins to sound like you're singing through a cardboard tube. If you're the guitar player listening to your singer, it's going to be perfect. But if you're the singer itself, to some people, not everybody, about half singers can't stand that. They can't use it because it sounds like they're talking like this now. And they either can't work around it or they give up, whatever. So almost all in-ear monitor systems are analog. Analog, unfortunately, you talked about sound quality. Analog radios, the sound quality is directly related to the RF signal quality, right? With digital, it doesn't matter. So conceptually, you're sending them 1 and a 0. A lousy 1 is still a 1. It never is sending 0.9 or 0.3. It's sending 1 or it's sending 0 or it's off. So it's always, it really doesn't, there isn't, conceptually, there's no distortion in a digital signal. Till it gets so distorted, the radio won't work. Up until then, it's perfect, then it stops. So you're good or you're off. With analog, as your signal quality changes, your fidelity changes, your frequency response changes. Your frequency response changes with level, and your just the whole amount of signal you got changes with distance. You probably can remember the old days when we listened to car radios and not X radio and XM, FM. As you drove further and further out of town, your radio got lousier and lousier. Well, if you really want to measure it, you can take your wireless microphone at 10 feet away from your antenna and then walk out 100 feet and record those two things and put them in something that'll analyze it. And it'll tell you that your signal from 100 feet away has lost some stuff that it had at 10 feet. So analog is definitely related to the quality of the radio signal it's picking up. And that's why it's really important to use circular polarized antennas, because the in-ear monitors, almost all of them are single-ended. They're not diversity. So you don't have another antenna to switch to. So as you're wearing your belt pack and moving and twisting, just the amount of twist that you put in your belt pack is changing your receiver's ability to pick up the signal from wherever it's being transmitted. So if you're using a whip or a paddle, they're fine if your belt pack doesn't move, right? We always have television stations mounted on a hill, antennas mounted on your roof, nothing's moving. So once it's dialed in, there's no polarization losses in the antennas, right? They're fixed. But when we started having satellites that we had to track, and that's of course going across the sky, so it's always coming at you at a different, your antenna's down here and your satellite's up here. My hand's moving. The angle's always changing, and so the receiving antenna's ability, if you move the antenna with it, that's how they used to do it. They just take that dish and move it, right? And your phone has a circular polarized antenna in it, because who knows how it is in your pocket. But anyway, circular polarized antennas for IEMs is really important because you're using analog IEMs. If they were all digital, it wouldn't matter as much, right? Because as long as you can get the signal. Now, it's still, paddles and whips are going to drop out before circular polarized antennas. But before any of them drop out, paddles and whips are going to be constantly changing the fidelity of your in-ear monitor. So you want to use circular polarized antennas. So I think I covered all the points in that. Did I?
Oh yeah, for sure.
Okay.
Very good insight there, Don. Now you've got one that's I think probably easier, since we answer it 10, 15 times a day.
Okay.
What is the maximum RG8X cable length from Combine 8 to CP beam?
60,000 miles. Well, no, at 8,000 miles, you've gone around the world once. So the answer to that is every additional inch of cable is creating loss of your signal power. So the answer is you can use it as long as you get enough power out the other end. So the question becomes, how much power do I need out the other end, right? So if you take RG8X and you're roughly in the middle of the UHF band and 550-ish or so, you're going to have 7 or 8 dB of loss in every 100 foot of coax. So let's say I've got 8 dB of loss going out to my antenna. I have 2 questions. How big was the signal when it started? And how far away are you going to be from your antenna? Because the answer to that is different if I'm only going to be 10 or 20 or 30, 40, 50 feet away from the antenna than if I'm going to be 300 feet away from the antenna, right? Because I've got inverse square loss there as well. So I'm losing signal through the air on top of that. So we can't just look at one piece. We have to look at all the components of the system together and how they interact with each other. So again, we recommend that you turn your IEMs to the lowest power that they will successfully operate. Again, if I'm on a stage and I'm 40 feet away, that answer is different than if I'm trying to get somebody on the other side of a football field, because I've got so much more loss. So I may have to turn up the power. In that case, I may need the power for the distance, although probably not as much as anybody ever thinks. And I may be able to live with the amount of intermod that I'm going to get because I'm not in Times Square. I've got more choices for channels. So there's not one answer to that. It all depends. And the other thing, so when everybody calls me and says, I get a question like that, I can tell you what the best practice is. What I can't tell you is what you might be lucky to get enough to get away with, right? Because you could do everything wrong in some places, or let's say everything not well in some venues, and it's not a problem. You can break lots and lots of rules and it still works. If you've gotten just the right spot, you could stick a coat hanger in the back of your receiver and make it work. There's just not very many of those spots anymore. So I can tell you what the best practice is if you want the most possible reliability, but I can't tell you what you absolutely need to make it work, because it might work here and 10 feet over, it might not work there. So if we follow the best practices, that's going to be as good as we can get. So I really can't tell you how long that coax can be. I can tell you the shorter it is, the less loss, and that's probably a good thing, less loss. It's not always, but almost always. So as short as you can keep it. So, boy, if I had to go any farther than 100 feet, I'd sure want to know why, but I'd probably rather keep it to 25 feet, as a first choice. Antennas like our CP beam, our circular polarized antennas have gain, right? So our circular polarized antenna, if you were to use a CP beam, let me add this, that has 10 dB of gain. So if you have 100 foot of coax, you still have more signal coming out of that antenna 100 feet away from your transmitter than you would if you'd have plugged the whip in to your transmitter. But you're now 100 feet away. That's your starting point, with more signal, not by much, but a little more than you would have started the other way. So, you just you have to see what works. You have a threshold that you have to cross, okay? And as long I should say you can't cross. You have a threshold you have to meet, right? So basically, and we go over this 100 times, you need to get the signal from your transmitter to your receiver about 20 dB more than the noise floor is. So again, You could use 100 foot of coax some places. You could use 200 feet in some places, and in some places you couldn't use 25. It depends what you're competing against. Remember, I said we can get you the signal there, but when we get it there, you have to. It has to play against your competition, and I never know what your competition is. So those are the things we have to consider. So I'm sorry, there's not a single answer to how far I can run a coax cable, both for my IEM antenna and my wireless mic antennas. Although for wireless mic antennas, you can use, back to our performance tools on the website, you can use the performance calculator, and that'll give you a real good idea. I think we have that in 25-foot chunks of how much cable you can use and different kinds of cable. So that I can do that for the wireless mics. For the ears, I can't really do it the same way. So so those are kind of the rules of thumb. Keep it as short as you can. And hope it works. I mean, that's that's really. I mean, there are some other. If we can got a lot of measurements and calculations, there's some things we can do, but it's not easy. I have to be there. We have to measure, but that's the best I can tell you with that.
Excellent, Don. Looks like we have about 4 questions left. We're still getting some live questions, so I'm trying to manage the time here. If we're not able to get to your question, please reach out to us directly after, and we're happy to answer. The next question is, any advice for people managing busy RF environments, 75 channels, that has TV stations activating new channels?
You got to measure frequently. Yeah, I mean, you don't have control over things that are around you. So, bandpass filters, you can block stuff outside the band pass. That's a good answer sometimes, and sometimes that's not because it's too close. You just have to frequently scan. If you're at church, you should scan every Sunday. Do you need to? Probably not. But should you? That would be the best practice, and scan very close to the time that you're doing it. For a big show, if I'm doing Elton John at the Enormodome, I'm scanning the whole time the show's going on because things change. If you're a church and you have a visiting band or something, who knows what they might bring with them that they don't tell you about until they turn it on and wipe out your coordination. So you want to scan as close to the time as you can, as frequently as you can. I know I still get, let me back up for a second. So when they got rid of the 600, so we all know they got rid of everything above 608 essentially, and now you can use 470 to 608. So when they did that, they took a lot of the television stations. They took over 1,000 television stations in the US, and they moved them down into the 500s. So that was all supposed to be completed by July of 2021. I think it's completed. It didn't actually happen because COVID and supply chain, and we had all kinds of problems. It mostly got done. And what didn't get done, some of the television stations got what they call STAs, temporary authorizations. And so they may have changed the channel, but they may not be using the antenna they're going to be using. And so when they put the real antenna that has more power and focused a little different, things are going to change. So these things are still changing. The other thing is that they add television repeaters. So if you happen to live, I don't know, in a particularly hilly area, let's talk about Atlanta, Georgia, my least favorite town to do Wi-Fi in. Sorry, it's just unpredictable sometimes. So because of the terrain, there's hill and valley and hill and valley and hill and valley and hill and valley. So they put the television transmitting antenna up on a hill, and it broadcasts over the top of all that stuff. But because it doesn't go down into the valleys because the side of the hill's blocking it, they put repeaters down in those valleys. And they're still putting repeaters up. So they're not 500 kilowatts, they're 15 kilowatts, but they're pretty close to you. They're a mile or two or three away. And that's still enough to wipe you out quite handily. So I get those phone calls. Hey, we had our system and it was working for 2 years, and all of a sudden we turn it on this Sunday and it doesn't work at all. Yeah, they dropped the television station on your head. So you have to scan frequency. If you can't scan, you can go back and use wireless system builder, right? So save your scan, print it out, look at it, and go look next Sunday and the Sunday after that and the Sunday after that, and see if it changes. It probably won't change frequently. I mean, if it changes once in a year, that would be a lot of change. It probably won't even change that much, but for some people it will. And so once you get that coordination, that's not good forever. That's good until something changes, and that could be anything. So the best you can do is scan and coordinate as often as you can. You don't always need to, but that would be the best practice, because you'll find problems before they actually happen that way.
All right. This is a good one, Don. How to best extend wireless reception for one or two wireless mics from a main room system into another further out room lobby.
How to best do it is you need to have a pair of antennas or a single diversity antenna inside every room. Every room that's walled off should have its own antenna. Or antennas, diversity pair of antennas. Does it need to? Not always, because radio goes through walls. You lose a lot. The question is, did you lose too much? Depends what the walls are made out of. If they're steel, you're not going to get much through them. If they're sheetrock and 2x4s, you'll get a lot more through them. You'll still lose 40% of the signal. That may be adequate. And it depends how many mics you got to use in the other room. If I got to use 2, or do I have to use 24? So all these things matter to what you might be lucky enough to get away with. I get this all the time. People with hotel ballrooms where they have those, or any place where they have those movable walls. Those are metal framed and they block a fair amount of RF. There may still be enough that leaks through. But the question is, what's the best practice? The best practice is an antenna that you can see from your transmitter inside every boundaried off room. That's the best practice. So if you want the most reliability now and for years to come, that's the other thing. You got to remember, what we do today and turn on today and it works today may not be working next year, because again, things change. They drop in a new repeater. Microsoft goes on that Microsoft Whitespace project, brings in more stuff. Things change. And so that's why you need to scan frequently.
All right, Don, last two, and you just hit on the one I'm going to ask now. Can you or Don expand on a comment he made about Microsoft transmitting broadband internet in the 500 band? First time I've heard that Microsoft is doing this. I'm assuming Microsoft is not considered white space device and has to move around wireless. How much do we need to consider this, if at all?
It is white space. So it's kind of interesting. So I believe it was 2013, the FCC. So before 2013, all wireless microphones technically required a license from the FCC. Since 1969, when they started selling licenses, they've sold like 1,400 licenses, and there's 3 million wireless mics in the US. So obviously, nobody's got a license. In 2013, they dropped the requirement for a license, provided you stayed under 50 milliwatts. There's a couple other little things. So basically, anything you can buy from anybody is legal according to the FCC. So you're below 50 milliwatts. And you're now legal. So that also said to Microsoft, you can build anything you want that stays under that, and you're legal. It's like, oh, well, we have countless billions of dollars to build new stuff that we can go out and sell. And so, if you live on top of a mountain somewhere and you have dial-up internet, that's no fun. You'd like to have broadband internet. You just don't want to pay $800,000 for them to run coax or fiber out to your house, right? So Microsoft came up with this plan. It's been active for, I don't know, 6 or 8 years. They ran it in Africa for 3 or 4 years. I think you can check me, but 4 years or 5 years ago, maybe, they started turning on in the United States. So they basically go to rural areas. They broadcast, they put internet in a pipe. They send it white space devices, and it's sort of spread spectrum. It jumps all over the place. So they're literally using any open frequency they can find for any amount of nanoseconds they can find to broadcast data, and then they jump to another frequency. It's like spread spectrum does for Wi-Fi. And so they would like to fill up everything that isn't a TV station. So depending on where you are, and then they broadcast that, because at 500 megahertz it goes, I don't know, 50 times farther than it does from cell phone frequencies, up 1.8 gig in that. Lower frequencies just go farther with the same amount of power. So now they can broadcast it a mile or 2 miles away to your house. You get a little box that gets this 500 megahertz white space radio into it, and then it converts it back to 2.4, and you just treat it like Wi-Fi in your house. They are on, last time I looked, so you can go look, it's on their website, Microsoft Broadband White Space Project. You can go look and see where they're on. But they committed, I believe, $13 billion to the project. So they're not giving up. They intend to offer broadband internet every place in the US it currently isn't, and maybe other parts of the world too. Like I said, I know they tested this for 3 or 4 years in spots in Africa before they turned it on in the US. So yes, it's active. Yes, there's a lot of money behind it. And, when they overrun us, they'll overrun us. When they completely wipe that out everywhere, then we're going to have to develop new kind of radios. And I'm sure we will. We've been working on that for 10 years. 10 years from now, I expect radios to be very different than they are now. But we'll just have to wait and see.
All right. Last and final question for this amazing session, Dawn. Thank you for your time and tutelage as always. How do you account for intermods created by two-way radios? How much influence do these devices have on your available spectrum?
Well, as always, it depends on what frequency. So you only have to worry about one way of the radio, essentially, the transmitter side of the radio. It depends on the frequency they're at. It depends on the power level they're at. And it depends how close you are to it. It's the same principle for all radios. Now, usually where we see this is security radios. It's called FMR, and they're generally, like, I don't remember the exact frequencies, 450 to 460 something. So they live pretty close to the low end of your available frequencies. You could tune down to 470, and they're pretty close. If you're tuned way up to 580, they're not going to interfere with you as much. In fact, maybe hardly at all. But they do. That's why I say, if you scan for that, if you put that information, that data into the coordination program, then it's going to consider that when it sets up your frequencies. If you don't do that because you scanned with your receiver, or you scanned with something that'll only do 470 to 608. I mean, that's better than just 130 or 50 megahertz block, but it's not looking at your security radios. So you also need to be keying those while you're making the scan. The other thing you need to do, not exactly an answer to this question, but is like, if your venue uses security radios, and it's unfortunate to say Many churches use security radios these days. Who would have thought? But anyway, you don't want those guys keying their FM radios when they get pretty close to your antennas. You're going to know about it, because even though they're not your same frequency, they got so much power that if they get close enough, you'll know about it. You get a big click in your system, a big pop. So you want to definitely tell those guys, don't be standing anywhere near my antennas when you're playing with your radios.